Okay, for section 3.1, it deals with exponential functions. The two most common types of problems you see in the homework are graphing an exponential function, like this one, and then being able to solve an exponential function using what they call the one-to-one property. So I'll do those types of problems for you today. So the first one I'm going to have you do or take a look at is graphing an exponential function. And so there's a process that you'll want to run through in terms of the steps. Now the nice thing is it's very similar to what you're doing when you graph a parabola. You know how like a parabola you look here to see, set that equal to 0 to figure out if you move right or left. This tells you whether you move up or down, and then the a value is important for a parabola, is not as much important for an exponential function, but the same idea. The x minus h, that's actually right here, it's up in the exponent. The plus k, that's actually there. So there's specific places that I want to look. Now, the book does this a lot, but there's always an implied number here if they don't give you a number, and that's implied to be 1. And the reason that's important is that's the y-intercept number. So here's the steps that I would run through. I'm going to do what I say is graph the original. I'm going to ignore all the shifting and moving and any reflecting and anything else that it does. I'm going to graph what the original function would look like. The original function has a y-intercept of 1 here. It has what we call exponential growth because this base number is bigger than 1. If it was less than 1, it would be exponential decay, and then your graph would look like this. Since it's bigger than 1, it's exponential growth, and it looks something like that. And I'm going to have you label that with a 1 to tell me that that is the original function without moving it or shifting it or doing anything to it. Alright, now when it comes to graphing the rest of it, I have to look for any possible reflections and then movement. Make sure that when you're looking for these things, you always do reflections first, then movement. If you do it the other way around, you unfortunately are going to be wrong. So reflections, that means, is the function negative in front? So do I see a negative in front here? I don't. That means it's not going to reflect over the x-axis. Do I see a negative on the actual x variable? Yes, I do. That means it's going to reflect over the y-axis. So this function now, according to the reflections, is going to reflect over the y-axis and look something like this. So imagine this function reflecting this way. It's going to look like this now. And I'm going to label that with the number 2. So if you want to, you can say that this reflects over y-axis. And then in terms of the movement, remember this is the x minus h. I want to set that equal to 0 and solve it. So if I subtract 2 from both sides, multiply both sides by negative 2, I get x equals 2. It's a positive number, so it's 2 to the right. The back number is just 1 outside parentheses, so that means it's moving up 1. So I took care of the reflections. Next thing I'm going to do is I'm going to pay attention to that point. It's the only point that I really know without plugging and chugging numbers. I'm going to move it to the right 2 and up 1. So that point is now right here. And then we understand, or we talked about it in class, that there is a horizontal asymptote here at y equals 0. This number controls the movement of the horizontal asymptote. If the function moves up 1, the horizontal asymptote also moves up 1. So there's actually a horizontal asymptote that's going to be here. And then the last curve that I drew was this one. I'm going to draw that same shape through this point. And that will be my final answer. And like I say, I usually make this one darker, just so that when I'm looking at it, I can say, okay, yeah, that is definitely the one that you're trying to tell me is your final answer. And I want that point. And so, like I said, the reason I want you to label it with the 1 and the 2 and the so on is this. When I look at this, let's say you didn't label it and I looked at this. I can probably figure out what you did, but in terms of the steps, it tells me exactly what you're doing. I can see the 1, so I know that you looked at the y-intercept and got the right number. I know you saw this was bigger than 1, so you knew it was growth. Otherwise, if you don't have these labeled, maybe I thought that was your first one. Probably not going to think that because this is your final answer, but it just helps me in terms of grading it. So please do that. And then make that last one darker, or just make this one number 3 so I can tell it's the last one. Alright, so again, what you want to look for is look at the y-intercept first, look at the base number to see if it's growth or decay, and then put your first function in. Then you want to look for reflections, which means you look for a negative in front of the entire function, or a negative on the x. If it doesn't happen, that's fine. If it does happen or they both happen, draw those in so I can see it. If you have to reflect both times, I would say draw that reflection and then draw the other reflection right away as like two separate graphs. And then the movement, if you want to shift to the right and draw a graph and then shift up and draw a graph, you can, or you can do both of them at the same time. But there is your graph. If you need help, again, by all means come in and ask for it. The other type of problem that you get is solving an exponential function where it's 1-to-1. Again, I can identify this as exponential because the variable is in the exponent. And what they mean by 1-to-1 property is that this is considered to be the base number. It has the exponent. There's, of course, a little implied 1 in the exponent, so 9 is the base. You want those two numbers to be the same, is what the 1-to-1 property says. So what you do is you usually take the bigger one and rewrite it using the smaller one. So I'm going to say that this is still 3 to the x minus 4, but I could say that 9 is really 3 squared. And now notice the base numbers are the same. And if the base numbers are the same, if these two things are actually equal to each other, then that means that the exponents are the same. And so I can say that x minus 4 has to equal 2. Go ahead and add 4 to both sides, and I'm going to get x is equal to 6. And if you plug that back in there, 6 minus 4 is 2, 3 squared is definitely 9. So that's the idea. Get these base numbers to be the same. So I look over here and I'd say, okay, that's the base number. Anytime you have a fraction, remember when we're simplifying, if you move something from the numerator to the denominator or vice versa, it changes the exponent. I can leave this as 2 to the x minus 3, and I can say that this is 16 to the negative first power, and that's the same thing as 1/16. What I would like to do is have all of my numbers in the numerator if possible. Alright, well, these base numbers still aren't the same, so how can I rewrite 16? Well, I can say that 16 is actually 2 to the 4th. Now 16 is to the negative first, so that means 2 to the 4th is also to the negative first. So on the left side I've got 2 to the x minus 3. On the right side, remember what you're supposed to do if you have an exponent on an exponent, you're supposed to multiply them, and that would be 2 to the negative 4th. And now that these base numbers are the same, that again means that the exponents are the same. And now I can just look at the exponents and solve. Add 3 to both sides, I get x is equal to negative 1. Plugging that back in, that would give me negative 4. The negative is what puts it in the denominator. 2 to the 4th actually gives me 16. Alright, and then the last one. Said I want to have everything in the numerator if possible, so I'm going to make that 9 to the negative first is equal to 27 to the x plus 1. This one's slightly different. There's no way for me to write 9 squared or 9 to the whatever power. 9's not going to go into 27 evenly in terms of powers. So I think to myself, what number goes into both of those that I can use? 3 does. I can rewrite 9 as 3 squared. That's still to the negative first power. I can rewrite 27 as 3 cubed, and that's still to the x plus 1 power. So it might not be that this number will go into that nicely using powers, but that's fine. You can still rewrite them, at least the problems that we're doing, you can still do that way. Alright, remember exponent on exponent, which means I multiply them, so this is actually 3 to the negative second power, is equal to, multiply those together, that's going to give me 3 to the 3x plus 3 power. And now that these bases are the same, now I can just ignore the base and set the exponents equal to each other and solve. So subtract 3, divide by 3, and x is going to equal negative 5/3. And so that is solving using the 1-to-1 property. Big idea. Remember, you're trying to get these bases to be the same, and then you're just using rules of exponents. Alright, I hope that helps. If not, please come in and ask for help.